Welcome back. Our topic today is going to be ray tracing and the formal definition of what is a ray and how do you trace it. In the previous lecture we talked about the Iconal Equation, which basically says I have phase functions, which we call iconals, as a function of three-dimensional space. If I set this equal to a constant, this represents an equiphase surface. And successive equiphase surfaces are one way to view how a wave propagates in space. And the key result from geometrical optics was the Iconal Equation, which said the gradient of that surface, basically the progression in space, magnitude is going to be equal to the index of refraction. And that was a high-frequency approximation to the Helmholtz wave equation. We had to make the caveat, though, that it wasn't necessarily only or exclusively a high-frequency approximation. It really is a change in field value relative to the scale of the wavelength. So you can ray trace low-frequency waves as long as the amplitudes are not changing on the order of a wavelength. So, with that, let's go ahead and start tracing waves. Okay, we're going to start with this constitutive relationship right here, where rho as a function of distance is going to be our ray path. Rho vector is a three-dimensional vector, a position vector, and it's a function of s, which is length along the ray path. Our rays are going to be defined as being perpendicular to our iconal functions. So this will progress like this, and we'll define that path by saying the derivative of the position as a function of s is equal to t, a unit vector that always points normal to the iconal. So we give it a little hat because it's a unit vector. So really we know that t is going to be equal to the gradient of s divided by the magnitude of that gradient, because it's a unit vector. And of course, by the Iconal equation, that means we could just divide by the index of refraction. Now, if you wanted a local approximation, of a ray trajectory, we would just have a starting point and that unit vector would point in a direction and as s increased you would project the ray path along that initial t hat. And of course, this is a local approximation unless we're in a simple medium that has homogeneous index of refraction. Remember that the index of refraction is the square root of permittivity and permeability. If the dielectric medium doesn't change and there's no magnetic behavior, that varies with respect to space, then this is a constant and you get straight lines. Of course, we want to deal with the general result where rays could curve if we have variations in epsilon and mu. So, what happens when we look at that scenario? Well, let's take the second derivative of our key constitutive equation defining rays. The second derivative of that trajectory is going to be equal to the change in that unit vector with respect to s along the path length. And it's important to note that the way that we've defined this, the length of that unit vector does not change, because this is path length s along here. There's no forward acceleration. There's only curvature when you change. So if you look over here at the differential element, at time or position s, I have a unit vector at 1 advance infinitesimal d sub s. I'm going to get a curvature in the perpendicular direction, which we'll call u hat, and the magnitude of that change is going to be kappa. So you can think of this as a measure of curvature. The bigger the k, the curvier the ray path gets. So going back up here, the second derivative of the trajectory is going to be represented by kappa u hat, and of course t hat times u hat is equal to 0. These are orthogonal, perpendicular to one another. So then that raises the question, if you do have changes in the medium, how do you calculate kappa and u hat so that you could develop an algorithm or some analytics that would allow you to calculate a curvy ray path through a complicated medium? Okay, so we already noticed earlier that t hat can be defined by this normalized gradient of the iconal, and of course this is index of refraction down here as well. So the index of refraction remember, this guy came from the constitutive relationship d rho ds is equal to t hat. If t hat is equal to this, I can write gradient of s over index of refraction and then move the index of refraction to the other side of the equation. That's how we got this result here. Now, let's do just a little bit more manipulation here. Let's take the derivative with respect to s of both sides of this equation. So by the chain rule, the left-hand side here becomes dn ds, or conversely, we could write that as the gradient of n projected onto the direction of the ray. Now, I've got dn ds times my derivative of the ray trajectory. Over here on this side, I have just plain index of refraction times the second derivative via the chain rule, which we already said had to be the curvature times mu hat, u hat. And that must be equal to the derivative of the iconal with respect to s. Okay, now we're going to apply a vector identity here to this term, the derivative with respect to s of the gradient of the iconal. We have an iconal. The gradient's going to point to the direction of increasing phase here, or phase progression, and differentiating that vector with respect to path length as you advance along the ray is equivalent to taking the gradient of the magnitude of the gradient of S. So recall, if this this derivative with respect to S is operating on a vector, you start with an iconal, which is a scalar. The gradient gives you a vector, and then the differential operator here gives you a vector as an output. Down here, we start with a scalar. We get the gradient. We take the magnitude, which gives us a scalar again, and once again, the gradient winds up with a vector. So this is just a basic vector identity from vector calculus. And it allows us to simplify the equation even more, because this term, of course, is the index of refraction. So this whole thing can be reduced down to a much cuter form down here, which says that I have an iconal function as a function of three-dimensional space. Phase is progressing. I have a ray trajectory. And what's more, I have an index of refraction that's going to be a function of space. And that, if I draw lines of constant index of refraction, I might have something like that. In fact, let's switch to multimedia colors here. So, if I take the gradient of the index of refraction, at any given point here, I'm going to have my ray trajectory, which points at t hat, and an index of refraction, whose gradient points in some arbitrary direction at that point. And this beautiful little equation gives me a tool for calculating what U and kappa should be. From this, we can say, oh, all I have to do is project that gradient into the t direction. That's my t component. The remainder of that gradient index of refraction vector, whatever term remains, has a magnitude n kappa and a direction u hat. So this is what I'm left with. This is what allows me to calculate these things. My u hat has to be equal to the direction of t hat crossed into the gradient n. That gives me a perpendicular component. And then when I cross that into t, that further gives me my u hat vector. And I think there should be some normalization on this equation, just to make sure that we get a unit vector out of it. But this will make everything point in the right direction. Once we've established the direction of the curvature of our ray, then I can calculate kappa by taking the gradient of n, subtracting off the ray component that projects in the t hat direction, and then normalizing 1 over the index of refraction, that magnitude. Very elegant way to trace rays. So this allows you to set up an algorithm that can march over time your analytical ray through a very complicated medium. Now, of course, not all media are complicated if n is a constant, I have a homogeneous medium, then the gradient's going to be 0, and kappa is going to be 0, which means straight rays. If, however, I do have a gradient, the stronger the gradient, the more the curvature, unless that gradient happens to be aligned already with the trajectory of the ray. If that's the case, then look what happens. This term, delta n, is basically equal to the magnitude of this. And so delta n minus the part that projects onto the t-hat direction will be 0. So I don't get any curvature. So in order to maximize curvature of rays, I have iconals and iso index of refraction lines that are perpendicular to one another. This will cause maximum bending. Now we'll have some applications later on of this, but I want to mention a couple things. Couple ways to use this analytical ray theory that we've developed. One way is to ray trace waveguides. And you can do the dielectric or the metallic variety. Let's talk about the dielectric variety first. If you have a dielectric waveguide, especially let's say this is an example from fiber optics. In fiber optics, we have the core and a cladding on either side. And the core typically has a higher index of refraction. You can have a stepwise profile where if you drag your measuring device and you look at the permittivity of the index of refraction that goes into the index of refraction, you have a low index of refraction here and then a higher one when you get into the core and then a low one again. So I've drawn a sideways graph with my index of refraction as a function of, in this case, it's, let's call it y by convention. And quite often the difference here is pretty small. And the reason for that is that you only want to support, for long distance fiber optics, a slightly higher index of refraction in the core. That will make sure that all of the other modes, all the higher order modes except for the fundamental, don't propagate here along the core. You don't get total internal reflection for all but the shallowest of rays that propagates off that cladding. And of course you can ray trace the solution to these things. You just have to make sure that the ray that bounces off there provides some constructive interference with itself that supports the mode that travels along there. Now of course one of the problems with this type of waveguide if you do happen to have multiple modes, is that modes, when we ray trace this homogeneous medium for a conventional fiber optic, if I have different modes with different geometrical optics launch angles, this path here, let me highlight it in green, this one, and then the black one that I've drawn, these ray paths may both exist inside the waveguide, but they may not necessarily have the same distance traveled. In fact, the way I've drawn this, the green one clearly has a shorter path down the waveguide. And if I have a source on one end, and I ray trace the result in this homogeneous medium, and I excite both modes, I find that I'm going to have dispersion. And that's basically a fancy word for echoes. I send data that was aligned here, and it's going to bifurcate into two pathways, one arriving at T0 and the other one arriving at T1. And that will cause some symbol interference when I try to detect the signal that was sent on these modes. Now, there's actually a clever way around this. Some people have invented graded profiles for the core in terms of index of refraction. So the index of refraction is at a peak in the center, and then it tapers gently to get to 0. And then you have the cladding, which is kept constant. How would you ray trace something like this, and what would it look like? Well, because the gradient of the iconal is equal to the index of refraction, and where all of my ISO material lines run parallel to the edges of the waveguide. Oof, those are horrible parallel lines. Not even a little bit. All my iconals, hopefully, are either perpendicular in this direction or slightly angled. This graded profile is nice because as you get to the end, or as you approach the cladding wall, the gradient of the index of refraction pulls you back in. And then you bounce down here, and then it pulls you back in. One of the other neat things, though, is that the gradient, the index of refraction also represents 1 over the velocity of propagation in the medium. In other words, this guy out here, when you're over on the edge of the cladding, you're actually traveling faster than you are in the middle here. So this speed out here is faster than the speed in here. So that if you were to launch another mode that, say, had a shallower angle of attack, it would wiggle around in here, and the length along that green line it would travel would still be less than the black line, but the dispersion would be minimized because the black line is traveling faster over here at its extremities than it is in the middle. So fast, slow, fast, slow, fast, slow, and things wind up, and the extra path length can be made up for the fact that it's not traveling like the green line, which is mostly slow. So if you make this profile right, usually something parabolic or hemicircular, you will create something called a dispersion compensated fiber. Another interesting use of ray tracing is to calculate refraction. Now, you're probably used to the idea of refraction in homogeneous medium with discontinuities, because that's how they teach it to you in physics. But there are some medium that are inhomogeneous, not unlike the cladding of this previous example. And one of my favorite examples to talk about is the planet Venus. Venus, of course, has a very thick atmosphere. The surface pressure is about 80 times higher than on the surface of the Earth. It means the atmosphere, which is composed of carbon dioxide, sulfuric acid, nasty stuff, is very dense and has a high index of refraction. But the refractivity profile of n, if I were to graph it as a function of height, starts out high and then gently rolls off. And we're not talking about a tremendous large value above index of refraction 1 of free space, because this is a gas, but it's much higher than Earth by comparison. And almost graph Earth as free space, even though the atmosphere tapers. You're talking about an index of refraction on the ground of 1.000 something, and then when you get out into outer space, it's 1 exactly. Here the difference is higher. And what that means is that an observer standing on Venus can look down at the ground and see a really interesting rocky surface that allegedly, due to extremely active volcanism, recycles itself every million years or so, much faster than the Earth. But you can also see over the horizon due to an effect called super-refractivity. In other words, if you trace those rays, where our ISO, let's try to draw our ISO index of refraction surfaces. If you were to look up, that ray that we trace gently bends down, and you can actually see over the horizon. So when you went out to survey, if I were to sketch this out, on Earth you might see some small rolling hills and some rocks. Probably go to the desert and see something similar than what you'd see on Venus. This is what you'd see on Earth. On Venus you would see this much higher horizon, where after a certain point your sight would be rocks and hills and valleys and small features that lay beyond the sightline horizon, so it would appear higher in the sky. You'd get like a bonus, a compressed vision of the material that was beyond the horizon that you would normally see on Earth. Very strange to compensate. It would feel kind of strange, like you were trapped in like a bowl or a crater, but the rim of the crater would actually be material that would be beyond the geometrical sight line to the Earth horizon that you would normally see. Strange to contemplate. But all traceable using this simple ray tracing kinematic equation that we derived up here. So next, we figured out the kinematics of rays, how they travel through a medium. Now we need to talk about amplitudes, and that's the subject of the next talk.